Hello, everyone, and welcome. I'm excited to have you here today. We're about to dive into the fascinating world of coordinate geometry. On this first slide, you'll see the title of our presentation, Coordinate Geometry, along with a brief overview. Over the next few slides, we'll explore key concepts, methods, and applications that will help you understand how geometry and algebra come together in this field. So let's get started. Let's take a quick look at the contents of our presentation. We start with the objectives, which will guide us through this journey into coordinate geometry. Next, we'll explore the coordinate plane description, giving us a solid foundation. Then, we'll delve into some basic points and the coordinate system itself. Moving forward, we'll examine the distance formula, a key tool for calculating lengths between points, and see how it applies in real-world applications. We'll also learn about the distance from the origin and the midpoint, which are essential concepts in understanding spatial relationships. The section formula will help us find points dividing segments, and we'll explore the collinearity of 3 points, understanding when points lie on the same straight line. Quadrants will be discussed to help us navigate the coordinate plane efficiently. Then, we'll look at an example of distance calculation to solidify our understanding. The area of a triangle will be covered, linking geometry to coordinate points. Following that, we'll see how these concepts apply in various applications. The presentation will also include an overview of the applications of the distance formula. Moving towards more advanced topics, we'll explore the applications of the section formula and collinearity. Finally, we'll examine the application of the area of a triangle, and we'll conclude with a thank you for your attention. Throughout this presentation, these topics connect to build your understanding of coordinate geometry, its tools, and its applications. Now, let's explore the key concepts on this slide, starting with understanding divisions in a coordinate system. We'll look at how the section formula helps us find a point dividing a segment in a given ratio, which is very useful in many applications. Next, we'll review the distance formula, which is essential for calculating the length between 2 points and the various methods we can use to do this efficiently. Finally, we'll introduce the area of a triangle, highlighting its importance in coordinate geometry. All these topics are interconnected and will deepen our understanding of the Cartesian coordinate system and its 4 quadrants, which form the foundation for analyzing geometric figures in a plane. Yes, coordinate geometry plays a very important role in our daily life. It helps us understand and analyze the shapes and positions of objects around us. But you might wonder, is coordinate geometry really that important? Well, think of it as using algebra to study geometric properties. By working with symbols and equations, we can describe and solve problems related to shapes and locations. The coordinate system is essentially the framework that allows us to do this. So, in simple terms, coordinate geometry bridges the gap between algebra and geometry, making complex spatial problems more manageable. This is why it's such a vital part of mathematics and practical applications alike. So, in honor of René Descartes' work, the coordinates of a point are often called its Cartesian coordinates, and the entire coordinate plane is referred to as the Cartesian coordinate plane. This naming pays tribute to his groundbreaking ideas. Descartes also proposed something really important, the idea that curves and lines could be described using equations through this technique. This was a major breakthrough because it was the first time algebra and geometry were linked in such a direct way. What this means is that instead of just drawing shapes and lines visually, we could now describe their positions and forms mathematically. The method of describing the location of points in this way, by using ordered pairs of numbers, was introduced by René Descartes, a French mathematician who revolutionized how we understand geometry. And this leads us to what we now call coordinate geometry, a system where the position of any point on the plane can be precisely defined by an ordered pair of numbers. This approach forms the foundation for much of modern mathematics and helps us analyze geometric figures in a very systematic and algebraic way. Let's start by looking at how we identify points on the coordinate plane. A point on the x-axis has coordinates of the form x, 0, meaning its y value is 0, and similarly, a point on the y-axis has coordinates of the form 0, y, where its x value is 0. Now, when we talk about the distance of a point from the x-axis, we call that the y-coordinate or the ordinate. It's like measuring how far up or down the point is from the x-axis. On the other hand, the distance from the y-axis is called the x-coordinate or the abscissa. Think of it as how far left or right the point is from the y-axis. To find the exact position of any point on the plane, we need both of these values, both the x and y coordinates, so we use a pair of axes. This pair of axes helps us locate any point precisely on the plane, which is fundamental to understanding and working with graphs and geometric figures. Now let's take a closer look at the axes. These axes are chosen arbitrarily, meaning they can be any set of mutually perpendicular lines that pass through a point we call the origin. Think of the origin as our reference point, where everything begins. The important thing to remember is that the axes are perpendicular to each other, forming right angles. As we move from left to right along the horizontal line, we're moving in the positive x direction. Similarly, moving from bottom to top along the vertical line takes us in the positive y direction. This setup helps us visualize and describe positions in the coordinate plane clearly and consistently. By understanding these axes and their orientations, we can accurately locate points and analyze geometric relationships within the plane. This foundational idea is crucial as we delve deeper into coordinate geometry and how it connects to the broader themes of this presentation. Let's take a closer look at the Cartesian plane. It's divided into 4 quadrants, which are numbered in an anti-clockwise direction. This means that starting from the top right, we move counterclockwise around the plane. An important point to remember is that all abscissae, or x values, within a specific quadrant will share the same sign, either all positive or all negative. Similarly, all ordinates, or y values, in a given quadrant will also have the same sign. This consistency helps us quickly identify the location of points and understand their relationships within the plane. Recognizing how the quadrants are numbered and how signs are distributed is foundational for analyzing graphs and solving coordinate geometry problems. Let's talk about the point itself. It is identified as an ordered pair, which you can think of as abscissa, ordinate, or more simply, x, y. The first part, the x-coordinate, is also called the abscissa. The second part, the y-coordinate, is called the ordinate. These two values work together to precisely locate any point on the plane. Essentially, any point can be uniquely identified by its x and y coordinates. This concept is fundamental because it forms the basis for understanding how points are represented in a coordinate system and how we can describe positions in a plane accurately. Remember, these coordinates are the key to connecting points, shapes, and graphs in a meaningful way, which ties back to our overall theme of understanding the coordinate plane. Now, let's see how we can apply the Pythagorean theorem to the triangle deltaptk. By doing this, we arrive at the distance formula, which allows us to find the distance between 2 points in the coordinate plane. First, note that QT is equal to y2 minus y1, and PT is equal to x2 minus. These represent the horizontal and vertical differences between the points P and Q. Next, we draw the segments PR and QS, which are perpendicular to the x-axis. From point P, we then draw a perpendicular line down to meet QS at point T. This construction helps us visualize the right triangle involved in the distance calculation. Now, the goal here is to find the distance between any 2 points, say P with coordinates x1, y1, and Q with coordinates x2, y2. This is what we refer to as the distance formula. It's crucial because it provides a straightforward way to measure the straight line distance between 2 points on the coordinate plane, tying back to our overall theme of understanding geometric relationships through algebra. Now, let's look at how we can find the exact distance between 2 points using the distance formula. To make this concrete, we'll walk through an example. Imagine we have point P at 1, minus 3, and point Q at 5, 7. Our goal is to determine the distance between these 2 points. This example will help us see the distance formula in action and understand how to apply it to any pair of points. Remember, mastering this will be essential for solving many real-world problems involving distances in coordinate planes. So, let's carefully work through this example to see the process step by step. Now, let's talk about the distance of a point P, x, y from the origin. The key idea here is that we can find this distance using the formula, the square root of x squared plus y squared. This might seem familiar because it's based on the Pythagorean theorem, which relates the sides of a right triangle. Essentially, if you think of the origin at 0, 0, then the coordinates x, y form a right triangle with the axes, and this formula gives us the length of the hypotenuse. This concept is fundamental because it helps us understand how far any point is from the origin, regardless of where it is on the plane. So, whether you're analyzing the position of a point or working through a geometric problem, remembering this distance formula is crucial. It connects to the overall theme of understanding how points are situated in the coordinate plane. Now, let's look at how we can use the distance formula to identify different types of quadrilaterals and triangles. When we have 4 coordinates, the distance formula helps us determine whether the shape is a square, rectangle, rhombus, or another type of quadrilateral. By calculating the lengths of the sides and diagonals, we can analyze their properties, like whether sides are equal or diagonals bisect each other at right angles. Similarly, for 3 points, the distance formula allows us to verify the type of triangle formed, whether it's equilateral, isosceles, or scalene. We compare the distances between the points to see which sides are equal. These applications are crucial because they help us classify shapes based on their side lengths and angles, connecting directly to the overall theme of understanding geometric properties through coordinate geometry. It's a powerful tool that simplifies the process of shape identification when working with coordinate points. Let's explore some important corollaries related to quadrilaterals. When we have a rhombus that is not a square, an interesting property is that its diagonals are unequal. This helps us distinguish it from a square, where the diagonals are always equal. To prove a figure is a square, we need to show 2 key things. All sides are equal, and the diagonals are equal as well. Now, moving on to parallelograms, there's a similar idea. If a parallelogram is not a rectangle, its diagonals will be unequal. To prove that a figure is a rectangle, we need to establish that opposite sides are equal, and, importantly, that the diagonals are equal. For a rhombus, the focus is on proving that all 4 sides are equal. And for a parallelogram, the key points are proving that opposite sides are equal or that the diagonals bisect each other. Understanding these properties and how they connect helps us identify and classify different quadrilaterals accurately. It's all about proving specific conditions to confirm the shape's identity. Now, to determine whether 3 points are collinear, we need to show that the sum of 2 segments equals the third. Specifically, we want to verify that a plus b equals c. To do this, we'll use the distance formula, which allows us to calculate the length of each segment based on their coordinates. By comparing these distances, we can confirm whether the points lie on the same straight line, which is essential for understanding their collinearity. This approach ties into the overall theme of geometric reasoning and problem-solving, helping us connect algebraic concepts with geometric intuition. Let's start by drawing the necessary constructions to apply triangle similarity. First, consider any 2 points, A with coordinates x1, y1, and b with coordinates x2, y2. Now, suppose we have a point P with coordinates x, y, that divides the segment OB internally in the ratio m1 to. This ratio is crucial because it helps us find the position of P along OB, and it's the foundation for the section formula. To visualize this, we'll draw the segment OB and mark the point P somewhere between A and B, such that the segments AP and PB are proportional to M1 and M2, respectively. Next, to understand the relationships better, we'll construct the necessary auxiliary lines, like the line through P parallel to certain sides or the median lines, so that we can set up similar triangles. These similar triangles will help us derive the section formula, which gives us the exact coordinates of P based on the ratio. Remember, the key idea here is to use these constructions to relate the coordinates of the points and the ratio in a way that allows us to apply the properties of similar triangles effectively. By doing this, we connect the geometric configuration to algebraic expressions, bridging the gap between coordinate geometry and triangle similarity. Now, let's talk about the midpoint of 2 points. A and B. The midpoint, which we'll call M, is essentially the point that sits exactly halfway between A and B. To find it, we take the x-coordinates of A and B, add them together, and divide by 2. We do the same with the y-coordinates. So the formula for the midpoint M is x-coordinate of M equals the sum of x1 and x2 divided by 2, and y-coordinate of M equals the sum of y1 and y2 divided by 2. This concept is really useful because it helps us find the center point between two locations, which can be helpful in many applications, like designing layouts or analyzing data. Remember, the midpoint is all about finding that perfect middle point, and the formula reflects that by averaging the coordinates. It's a simple yet powerful tool in coordinate geometry that connects beautifully to our overall theme of understanding spatial relationships. Let's consider any triangle, which we'll call ABC. Its vertices are points A, B, and C, with coordinates at x1, y1, B at x2, y2, and C at x3, y3. This setup helps us understand how to find the area of a triangle using the coordinates of its vertices. The key idea here is that the area can be calculated from these coordinate points, even if the triangle isn't aligned with the axes. This method is very powerful because it allows us to find the area directly from the given points without needing to measure sides or angles. As we move forward in this presentation, understanding this coordinate-based approach will be crucial for solving more complex geometric problems efficiently. Now, let's look at how we can express the area of triangle ABC in terms of trapezium areas. The key idea here is that the area of triangle ABC can be broken down into the sum and difference of areas of specific trapeziums. Specifically, we see that the area of deltoAB equals the area of trapezium ABQP plus the area of trapezium BQRC minus the area of trapezium APRC. This approach allows us to use the known areas of these trapeziums to find the area of the triangle indirectly. It's important to understand that these trapeziums are constructed based on the coordinates of the points involved, which makes this method very useful in coordinate geometry. By calculating these trapezium areas, we can derive the area of the triangle without directly applying the traditional formula. Additionally, this method can be expressed more generally. The area of triangle ABC can be formulated using the areas of trapeziums derived from the coordinates. This technique is quite powerful because it leverages the properties of trapeziums to simplify what might otherwise be a complex calculation. So the key takeaway here is that by dissecting the figure into these trapeziums and understanding their relationships, we gain a flexible and often more straightforward way to calculate the area of a triangle in coordinate geometry. This ties into our overall theme of using geometric shapes and their properties to solve area problems more efficiently. Let's talk about how to practically apply what we've learned. First, you should mark the coordinate axes on your city map. This helps you create a reference system for measuring distances. Next, identify and locate important landmarks like the bus stand, railway station, airport, hospital, school, your house, and even natural features like a river. Once you've marked these points, you can determine the distances between them using the coordinate system. This approach not only makes navigation easier, but also illustrates how coordinate geometry can be used in real-life situations. Remember, understanding these concepts helps us solve everyday problems efficiently and connects the mathematical ideas to the world around us. And that brings us to the end. Thank you all for your time and attention today. I hope you found this presentation insightful and useful. Remember, the key points we discussed, whether it's the core concepts, the strategies, or the practical applications, are all connected to our overall goal of improving and innovating. Your engagement and curiosity are what drive progress, so I encourage you to take these ideas forward. Thank you once again for being such an attentive audience.